So, hello everyone. This is the third section of today of the CompleNet. We will have 4 presentations. We will wait a bit for 2 of the speakers to come in, but I would like to ask if Chico or Diego wants to begin this section. And then we can kind of change the order just to use the time that we have now.
So we can start with, in the order of the people that are here. So I think we have to start with Chico Camargo.
Right? Okay, that's fine. Okay, so just some rules. The speakers will have the ability to share the screen and to talk and to show the video. Please, if you are not presenting, you can turn off your video so the lives is better for us and the connection is better for us. Sorry, and please respect the time. So each speaker has 15 minutes to talk and 5 minutes to answer questions. I will tell when the speaker have 5 minutes left or 1 minute left. You can always put your questions on the chat on YouTube. I will check and then I will ask the speaker in the end of the presentation. And of course, the people that are not presented are not allowed to talk, so we don't have any problems with the connection and the audio. So thank you so much for coming in. I will start with Chico then. Is that okay, Chico?
Absolutely.
Thank you so much. So can you please share your screen?
Yes.
Thank you so much.
Lovely. Do you see my screen?
Yes, perfect.
Fantastic.
So I will track your time and I'll let you know when you have 5 minutes and 1 minute left. So feel free to start now. Thank you.
Splendid. Thank you, Mariana. So I'm really happy to be talking about this here at CompleNet. This is work that I completed a while ago and I was really looking forward to speaking about it. It's the kind of work that sits not in a field that's sort of hot and exploded, but rather in something that's still sort of getting warm. It's some work that I developed during my PhD. And at the time, there really weren't many people talking about genotype-phenotype maps. So I hope I can share a little bit of that with you today. So to start with, this is a talk about biology. So I thought I would just include the mandatory biological slide, this nature. Well, nature, as you probably know, is just full of all sorts of weird and amazing phenomena. There's a strawberry there, there's a rolling panda, which is my personal favorite, and all sorts of things done by evolution, development. But most of all, for what matters to this talk, all of these things are possible because of gene regulation. Gene regulation, for those who are not very biologically minded here, is essentially when a gene turns another one on, and then that gene, well, its DNA gets transcribed into RNA, which gets translated into protein, and ultimately that makes you. When the gene is off, nothing happens. And, well, you could think of genes really, for what matters in this talk, as little light bulbs. This is an example of behavior that's coordinated by gene regulation, the division of cells. Here's the fission yeast, and that little thing has about 5,000 genes. We humans have way more. But to give you an idea, this is a picture of the genes in the fission yeast, and you can think of that as really a constellation of little light bulbs flicking on and off, every part of them, every cluster of these light bulbs just coordinating different behaviors. And well, the way this happens is that one light bulb, one gene might turn on, and it might turn another gene on, and then that might turn other genes on and on and on. Maybe those genes might turn other genes off, and it's a huge mess. And when you start thinking of all the ways, all the multiple ways in which this can happen, well, there are many combinations of circuits you can draw, many ways to wire a gene network. In fact, for the fission yeast, if you were to just represent every gene network as some kind of adjacency table where a plus means gene A is turning gene B on, a minus means it's turning it off, so it's repressing it, and a 0 means no interaction. That would be a 5,000 times 5,000 table in which every cell can have one of these 3 possible values. So the number of ways in which you can wire that gene network, well, that'll be 3 times 3 times 3 to the power of 5,000 times 5,000. And that is a huge number. That's more than the number of stars in the universe or the number of subparticles in whatever. This is what people literally call a hyperastronomical number. And as vast as this is, it still begs the question of how nature even came up with that number in the first place. I mean, not with the number, but with the right combination. How did it find the fish and yeast? I mean, we can say, sure, it's evolution, but still, how did evolution find one needle in such a gigantic haystack? Well, let's kind of go at that question slowly. Let's think of this through the perspective that's called genotype to phenotype maps. That's a perspective that's actually much more convenient for people that come from a mathematical modeling background. You can think of a genotype as a coordinate, and in this case, it's a 2D coordinate. It could be latitude and longitude. And the phenotype is going to be orange, for instance, or could be red or yellow or blue. In fact, if I make this a little more fine-grained, you know, latitude and longitude could be your genotype, and your phenotype could be the country where that coordinate falls. So in this case, the phenotype would be China. And that perspective makes it easy for us to translate a lot of questions about dynamical systems to questions about evolution and vice versa. So in the case of the yeast cell cycle, well, first thing, the way to make a genotype-phenotype map is to get some kind of model of it. And here's an example of such models. It's a Boolean model where every gene can either be on or off, and every gene can turn another gene on or off in the way it's described. Here, the red dashed arrows and the green continuous arrows, they mean repression and activation. And the yellow loops, they just mean when the gene is activating itself. This is a network made of 10 genes, think maybe 10 plus the start one, and it represents a collection of genes that regulates the cell cycle. And now instead of 5,000, you have 10. So that's kind of easier to hold in your mind. And the way this model works is through, well, what's called Boolean threshold networks. So there's the other part of the title. That's what's represented in the formula there. And essentially it means that genes will affect the state of another gene depending on their own state. So if you have 3 genes regulating a 4th one, and 2 of them are turning it off, 1 of them is turning it on, the result is that it's going to turn off. Same if you've got 3 of them turning it on, but actually one of the genes that's regulating the 4th gene is off. Well, you can see there, 2 turning it on, great, it turns it on. And you can even have a balanced situation where the same number of genes is trying to activate or repress the gene kind of that's downstream. And the result of that is that nothing changes. That's the essence of a Boolean threshold network. And it's quite convenient for the modeler because then the whole dynamics of this network is encoded in its adjacency matrix, which is a directed network, but that's it. All of that, the biochemical dynamics is boiled down to this in this model. And actually, it's a kind of model that works pretty well. The paper I showed you with, well, the diagram I showed you with the red and green network, it actually has been paired with experimental data showing that it really does work. So that's what we're going to use here. You can make beautiful diagrams and phase diagram plots just showing how a certain state can take you to another. Sometimes 2 states of the same network can lead to the same state, and that makes you think of bases of attraction and eventually attractor states. Right. So to sum it up so far, a genotype as defined here is a network and how it's wired, and the phenotype is a map of what states lead to what other attractors. That's how I'm going to define it here. You can define a phenotype in multiple ways, but for the study that I'm explaining here, that's how I've defined it. So if you've got a network like this one, you've got 2 genes, one that's turning itself on and turning the other one on, and the other one that's just turning the first one off, and you've got a state space that's like that. So when both genes are off, it stays off. When both genes are on, then one of them turns off, etc. Then that's a picture of the whole state space. Right, just close this. So you cannot enumerate all the 3 to the power of 5,000, etc. images, gene networks, but you can look at smaller spaces. Here, for this paper, I decided to look at all the networks with 4 genes, whereas in other pieces of work, I've actually decided to sample larger networks. The reason to look at the whole space is to actually have an idea of which phenotypes are really underrepresented and which phenotypes are really common. If you were to sample an actual sized network with hundreds of genes or at least dozens of genes, effectively you'd only find the most common behaviors if you were to sample random ways to wire that network, for instance. Here we've decided to enumerate all the ways to wire a network made of 4 genes and see what you get. Well, first result is that often when you rewire a network, you just produce the same phenotypes. Here on the right, I made a map that's more or less meant to represent what I had there in the map with China and all that. Every coordinate here, every XY coordinate represents a genotype, and circles with the same color represent the same phenotype. So when multiple genotypes produce the same phenotype, here they're represented in the same color, and on the plot on the left, they represent a dot. Actually, they represent many dots. So when, they represent 1 dot. Many dots is in another plot. Here I've got all the phenotypes that you can find with 4 genes, and it's—
You have 5 minutes left.
It's over 1 million phenotypes, and some of them are very frequent. They correspond to many, large fractions of genotype space. But actually, as you see here from this long tail, is that most phenotypes are just smaller and smaller. This distribution of genotypes over phenotypes is really uneven. You find a lot of small phenotypes and a few large phenotypes that are orders of magnitude larger than everything else. Other properties you find is that these most frequent phenotypes are also the most robust ones. If you have any mutation to them, if you change 1 bit in the wiring of the network, the result is still the same phenotype. Other results, and I'm happy to discuss all them later, is that these largest phenotypes, so in my drawing on the right, that would be the red one that corresponds to the biggest fraction of genotype space. Those larger ones are also the most evolvable ones, meaning that if you are a genotype sitting on this large phenotype, you actually reach a lot of other phenotypes. That would be equivalent to saying that the largest countries are the ones that have the most neighbors. The spatial metaphor actually applies in this case, meaning that you can be at the same time very robust, meaning that mutations are likely to not change you, but also very evolvable, meaning that your phenotype is also likely to kind of give way, it's likely to lead to many new other phenotypes. That's something where biologists took a while to kind of understand how that could be possible, how it could be at the same time very robust and very evolvable. And finally, just to finish here, if you were to look at every attractor corresponding to every initial condition of the network and say, oops, if you were to just write that down as a binary string, well, you can calculate the complexity of a phenotype by trying to compress that string. If a phenotype produces very often the same attractor, then that is a simple phenotype. You could kind of measure it using the Lempel-Zip compression algorithm, which is the one behind WinZip. But if a phenotype actually produces many attractors and there's no particular order or pattern, the resulting binary string will actually be very complex. This way we have a measure of how complex a set of attractors is. For more on that, of course, check the paper. And here we did the same scatter plot of how frequent a phenotype is, meaning how much of it is in the genotype space versus how complex it is. And you see there's some kind of trend where the simplest, the lowest in complexity are also the ones that are highest in frequency. And that's it. This is the kind of stuff that has been found in previous papers. You can check out this one on simplicity bias. There are many other systems where you find this trend of, the simplest outputs are the ones with the highest probability. It's something that's found in many biological systems and even some other parameter to behavior maps. Quite intriguing. And well, this actually affects evolution a lot, because if you have, for instance, You know, say that you've got a lot of possible mutations, but some mutations are very likely to happen and they lead to the same results. That's kind of like having loaded dice. If you throw dice that often throw you a 4, this biased variation, so variation that often gives you simple phenotypes, that's also going to affect natural selection. Anyway, I'm running now, so I'm going to stop here. I'll just say thank you to all the funding. And if you're interested in this paper, just check the link here, Boolean GP maps. Thank you very much.
Thank you so much, Chico. Very easy to understand your presentation. I really like your examples.
Thank you.
So I have 2 questions. The first question I will read from the Zoom, which is, how can we apply this analysis in other populations? What specific type format of gene expression data is needed?
Right. So fortunately, I didn't need any type of data on gene expression here. In this case, I looked at a specific model. To apply this kind of analysis, you need essentially 2 ingredients. One, some kind of input to output or genotype to phenotype space where you can map it. So for instance, there's an experimental study where they were looking at transcription factors. They tried all the sequences for a small transcription factor. So it was, you know, a number like in the millions, but it was still large enough that they could try, I mean, small enough that they could try them all in the lab. You need that, like the ability to map the input, and you need, and then there comes the important bit, you need an output whose complexity varies. If your output is just yes or no, or like blue or red, then you can't have the x-axis in the complexity plot. You need an output that has a variety of complex phenotypes, of complex results. That's why anything with a shape or anything with a sequence, with a spectrum is quite interesting. If you can measure the complexity of your output, and if you can map the input space, there you go. That's all you need. So in this sense, the requisites aren't even biological. You can do this kind of stuff for actually very non-biological systems at all. We've done a little bit of that in one of the papers I cited too.
Okay, perfect. Thank you so much for your answer. So now I would ask Ronaldo to ask his question.
Hi, Chico. Thank you for the presentation. I'm curious about this modeling, right? So it's not, I guess, not necessarily about your results, but you said that this has been shown experimentally to be a good model, a good representation on those binary networks and those activations. So I'm curious about the uncertainty here, right? So because since you have one thing that activates another, how does this uncertainty propagate? I mean, how can you use those models to, I mean, models are used for, I mean, I guess perhaps to do predictions as well. And if those errors propagate, you end up having something, I guess, 3 layers down that it's not necessarily correct. Am I going the right direction here? So can you, just curious here how the uncertainties are quantified in a sense?
Yeah, I think that is an absolutely important element whenever you're doing work in systems biology, which is the case here. The thing we did was to take a model that was already sort of certified and valid and validated and many times, so like we could trust that model. In this sense, we kind of outsourced the problem. But in making the model of a gene network, especially in making such a simplified model, like turning gene activation into a binary thing, I feel that the best way is to really be clear in what you are defining and what counts and what doesn't, and be clear in what you are ignoring. This model that we actually used, it is the simplification of another much more complicated model which we studied separately, that had the whole curve of the concentration and activation of every bloody molecule in the system. And they made a simplified model of a subset of the system, which they knew that could be simplified in that way without losing too much. But I totally agree with that concern. And I think there's no easy answer of just do this. Rather, my recommendation is always write down and always be very aware of the things you are choosing to ignore, because these systems aren't very noisy.
Thank you very much. Yes, thank you very much.
Thank you.
Thank you so much, Ronaldo. Thank you so much, Chico. I will ask now for Sam Nallaperuma, sorry if I pronounce incorrectly, to take over. And then after her presentation, I will ask Nandini to present, and then we will follow with Diego's presentation. Okay, I'm just letting you know because we changed a little bit the order. Thank you so much.
Thank you, Mariana.
Thank you.
Can you see my screen?
Yes, perfect. Thank
Okay.
you.
So this work is sorry.
So I will let you know when you have 5 minutes and 1 minute left. And just to let you know, your presentation is not in the presenting mode. So if you want to, yes, exactly.
Yes, thank you.
Thank you so much.
Thank you, Mariana. And so I'm Sam Nallaperuma from Uni Cambridge, and so this work is the work that I contributed when I was with my previous research group at University of Exeter, and our collaborators, City Science Exeter, and thank you. I would like to thank CompleNet 2020 organizers for the opportunity for us to present our work in this CompleNetLive virtual conference. And also, I would like to thank our contributing partners, Exeter County Council and Oxford County Council and the Light Food Company for their valuable data and feedback provided for this work. This is actually a real world application that we try to optimize the signal timings in a real world transport network. So since
Sorry. So I just want to let you know that it's not full screen right now. So if you want to change for full screen.
Actually, I'm doing this Google Slides. So I think this is the mode that I could get. So you see my slides by the side.
Yes.
Yeah, so this is like the full screen in Google Sites because I'm using Google Sites. Because I have a video here. So
Okay, so I will leave in this way.
okay,
Thank you so much.
okay, thanks. So since this is a shorter presentation, I will provide a generic overview of the project and some key results. For the technical details of our approach and our experimental setup, I would kindly refer any interest viewers to our paper in the CompleNet proceedings. So this project has two main components. One is the optimization framework, where we optimize signal timings for a transport network. And a core part of this optimization framework is a transport model that we use. So since this is a real world application, we considered more realistic transport model. So we developed our transport model, which includes different type of vehicles and a real world map uh, using a microsimulation mod, open source microsimulation model called Sumo. And we validated this with real world data. Unfortunately, because of privacy policy issues, I cannot mention the exact names of the geographical locations, but we have used real world data. So and this model provides as output for a given network, for a given signal timing plan, delays, the total waiting times for all the vehicles within the network, and the fuel consumption for all the vehicles, and carbon emissions. So these are our performance criteria for the optimization framework. And for the optimization, we employed evolutionary algorithms, which is a meta-heuristic approach, and also hyperheuristics. And we also considered state-of-the-art signal timing optimizer called Webster method, where it considered only one particular traffic light individually. So the difference between that approach and our approach is, in our case, we consider the whole network at once, all the traffic lights within the network as a whole. So if we go to some case, we considered several case studies based on small scale towns and also larger cities. So for this particular town, which has 8 traffic lights, and this you see it's an actual map of the city, but I cannot mention the name. So here we obtain the result shows. So in this blue line mentions shows the Webster method, which is the it's usually used by many transport engineers, as we heard from actual county councils. The Webster method they use within their systems, and the results obtained using our evolutionary approaches and hyperheuristic approaches for the total waiting time, it shows a significant reduction, 30 and 31% for this particular case study compared to the Webster method. And also another town we considered for case study 2. That's also some smaller scale town. And here the results also follows a similar pattern. So we see they are significantly better. The waiting times obtained by hyperheuristic is even significantly better than genetic algorithm. And they both are significantly better than Webster method. So this is another town. Well, let's call it town C, and the results also shows the similar pattern as the previous towns, and also for town D, and also we extended, because in the current literature most studies are based on small scale towns, and so they haven't considered larger cities. So in our case we considered actual a large city with a lot of traffic lights. So this is one sample large city, and for this case also we obtained a significant improvement over the classical Webster method for genetic algorithm. And we did another experiment to see like whether there's an impact of particular subsets of traffic lights, particular location of on the overall performance. So in this case, it's more like a sensitivity analysis. So we tried, we vary only a signal program of only one traffic light at one experiment, and let the others fixed, and see how much fitness, I mean how much waiting time reduction we can achieve at the end. So you see certain different these numbers, they are the IDs of the traffic lights. So some are better than the others, so some are more sensitive, they have more impact on the overall performance. And when we consider the map, so this is the respective geographical representation of these traffic lights, and we see that certain one with lots of edges is a larger junction that has the one with the higher sensitivity. So this was then we presented these results to the actual transport engineers, and they also with their experience uh, told us that this is the case. I mean, these particular areas are prone to higher traffic jams, and I mean they have higher density of traffic. So it is our results comply with the real world experience. And then we further extended this optimization framework to consider different objectives at once to understand the trade-offs. So we considered the delays, or the total waiting times of the vehicles, and the fuel consumptions and carbon emissions. So we considered all three at once using an evolutionary multi-objective optimization algorithm. uh, in this particular experiment, we use NSGA2, a popular multi-objective algorithm, and we saw the results that there is a positive correlation between fuel consumption and carbon emissions, and also there was, but at the end we could see uh, some uh, some results that we could improve journey times by 6%, or we would see alternatively that we could improve emissions and delays. So if we try to, so there are small trade-offs at the end. So these results show the final solutions at the end of the optimization process. So there was a positive correlation at the beginning, but there at the end of the optimal set of solutions, we could see some trade-offs between the delays and fuel consumption and the carbon emissions. And so to sum up, this work, we understand the effects of signal timings of a broad network on performance, and we consider different performance matrices, waiting times, fuel consumption, and carbon emissions. And our results show that we can have significant improvements in these factors with using optimization approaches that considers the network as a whole, compared to the state-of-the-art approaches where they consider the signal lights separately. And also, as future work, we would like to extend this on more different geographical areas, and also to consider dynamic scenarios like accidents and road closures. To, so to give a simple idea, I think this might, so here, so we try to, we recorded the performance of the waiting times. You can see vehicles before and after the optimization. So so
You have 5 minutes left. Thank you.
this shows the after optimization. So thank you very much.
Thank you so much. Very interesting topic.
Thank you.
I was wondering here if you want to actually analyze socially how is the effect of the changes on the traffic, because nowadays I work with inequalities, and I was wondering, even though you are reducing the carbon emissions, you are helping, you are actually decreasing the time that people are spending on traffic, but is this reduction only positive for one specific income group, or one specific gender, what would be the social effect of this change? I don't know if you will do something in this topic, but I think it's really interesting to analyze socially what is the impact.
Yeah, that's really interesting. Actually, I will remember futures, because for this one we generically considered we need to improve these aspects into the model, because current model is rather simple. We have like different type of vehicles and area, but yes, it will definitely be interesting topic. Thank you.
Thank you so much. So now I would ask Hugo to ask his question. Are you allowed to?
Yes.
Yes, thank you.
Thank you, Mariana. Thank you, Sam. My question is in line with what Mariana asked. I didn't quite understand your simulation, but my question is your model, like, are the travels time resolved? Are they time dependent, or like what are the times of the day and what direction the
Yes.
flow is?
Yes.
And
Yes.
if that's the case, what travel demand model did you use to generate these travels?
Yeah, so here you go. As you see, the video shows like 9 to 10. So we just considered one traffic peak time, and so we could like consider different like total day or different times. So we consider peak and off peak as our train the model. So we got like peak times, and then the middle off peak, and again afternoon peak times. So that's like how we models. And to validate, we got actual traffic data from, I can't mention the names of the cities because of privacy policy, but we modeled their demand data and the waiting time values. So we validated our model based on the for the peak times and off peak times.
So just one follow-up question. Did you also consider if these trips, they arrived at the destinations that they had originally and the average travel time? Because that might be the case that you might reduce their waiting times on the traffic lights and their overall gas emissions, but did it actually reduce the average travel times of those trips?
We considered so we have the scope, the limit of the geographical area we consider. So the trip we consider for they start from A and to the B. So the trip ends at the position B. So we reduce the travel time between these two points. So for each vehicle, we have the starting and the source and the destination.
Okay, thank you.
Thank you. So now I would like to ask Ronaldo to do his question.
So Mariana, so between your question and Hugo's question, I think she already answered what I had. So thank you.
Okay, that's fine. So now we will move to the presentation of Nandini. Nandini, can you start sharing your screen?
So I just made Nandini a co-host, Nandini, so I should be able to.
Okay, thank you.
Can you see it?
Yes,
Okay.
perfect. Thank you. You can start now. I will let you know when you have 5 minutes left and 1 minute left.
Okay, great. So hi, my name is Nandini Iyer. I'm a first-year PhD student at the University of Exeter. And today I'm going to be talking about the network science approach we took to characterizing the dynamics of academic affiliations. This work was done during my undergrad as part of the Amalthea REU program, which was funded by the NSF. It was also done in collaboration with Josemar Faustino and Juan Mendoza. So we know science to be an expansive discipline, one that both directly and indirectly impacts many fields and society at large. However, the factors that influence the development of science remain extremely subtle, ranging from factors such as research funding to the emergence of hot topics. Ultimately, what we want to understand is why science develops in the way that it does, so that we can better identify ways to aid scientific growth. In addressing this question, we take a sociological approach, assessing science with respect to the humans that are driving these scientific discoveries. We study scientists in the context of their environments, specifically the institutions or universities with which they are affiliated. In studying the growth of science, we use research publications as a proxy for scientific progress, specifically looking at scientists within the realm of the computer science research area in order to analyze how their switches in affiliation impact the development of science. So for example, if an academic was entering a new university, we wanted to understand the symbiotic relationship of this academic and their new environment. For example, does the academic inspire existing members of the university to start publishing in areas that this academic is already well versed in? Or conversely, does the university convert the academic and to start publishing in areas that the university is strong in? And asking these questions, we pose our overall research topic: what is the effect of academic affiliation exchanges on the scientific output? I'm going to address this question by briefly touching upon our data cleaning process, as well as how we created our network to represent affiliation exchanges between institutions. Then I'm going to talk about how we created a new classification scheme and how we apply that to our network in order to understand scientific growth with respect to topic distributions as well as topic variety. Then I'm going to finish with concluding remarks, and then we'll have time for questions. So our original data set was collected by Pramod and consisted of a subset of ACM publications ranging from 1966 to 2012. Our biggest issue was that different names of institutions were used to refer to the same institution, and all sorts of variations were used throughout the data set. The issue with this was that it led to a misleadingly high node and edge count in the network, which implied false affiliation exchanges when really the academic was staying in the same institution. And this was primarily due to minor inconsistencies such as spelling or punctuation and how affiliations were listed. We addressed this issue over the steps detailed in this workflow. Ultimately, what this workflow did was it aimed to unify institutions that were previously regarded as distinct because of minor syntactical issues. This left us with our final data set in which we were able to reduce the number of unique publications by about 95%, while only reducing the number of unique publications by 13%. So with this data cleaned, we were able to start constructing our network. We'd use nodes to represent institutions such as universities or major research hubs. And the edges between these nodes would be weighted as well as directed in order to represent the number of academics moving from one institution to another. We would construct a network for each year in order to analyze the exchange of affiliations as a time series. So we applied this network structure to our data set, and on this slide we show information regarding the networks for the first year of each decade. What we can first see is that the node and edge count are progressively increasing as time goes. And this indicates a growth of network size as well as growth of scientific publications within the computer science area. Additionally, if we look at the second to last column, that measures the average clustering coefficient, which measures the extent of connectivity between nodes in the network. And the last column, which measures the average path length, which is the mean number of hops between any two pairs of nodes in the network. The combined low values of these two columns indicate properties that are consistent with those of small networks. Additionally, their low variability over a long series of time shows or indicates that there's an underlying stable process. So if we, in the plots below, we plotted the complementary cumulative distribution function for the weighted degrees of the network. That is the inflow and outflow of academics for an institution in the 4 years that we're looking at. And then we also plotted the betweenness centrality, which measures the centrality or the influence of every node in the network. What we can see is that there's greater variability when considering these metrics when, with respect to time, as compared to the average clustering coefficient and the average path length. With these networks constructed, we wanted to see if we could identify any communities or clusters based on the movements of academics between institutions. We did this by applying a hierarchical stochastic block model to the networks we had just created. And the first thing we can see here is that there is a significant evolution in the community structure. Additionally, if we look at this with respect to the countries of each institution, we note that the US as well as Asian and many European regions comprise most of the communities that were detected. Additionally, American institutions were present in the majority of communities that were inferred. And they appeared to be they appeared to have an exchange of academics with institutions from all over the world. Finally, if we focus our attention on the 2000 network, we can see a detached community that's mainly comprised of institutions from America. However, shifting our attention to the 2010 network, we can see this community split up into smaller, more delineated communities, implying a more an influx of exchanges of academics between smaller subsets of the 2000 community. So with these networks, with community structure, like with the development of the community structure having been analyzed over a series of time, we wanted to understand how these academic movements impacted scientific growth with respect to topics. The way we did this, our issue in doing this primarily was that topic classification in our dataset used ACM classes. And the problem with that was the ACM class structure underwent significant changes, notably in 1998 and 2012, which motivated us to create a new classification scheme for consistency. In order to do this, we got publication data from Semantic Scholar in order to map the publications in our data set to their respective abstracts. From there, for topic modeling, we used a stochastic block model in which we needed to create a different network of words and abstracts in order to represent the content of the publications we had access to. So this is a sample of the bipartite network that we created, in which nodes were represented by words and abstracts, and an edge existed between a word and an abstract every time that word appeared in the abstract. In order to retrieve the hierarchical structure of topics, we applied the stochastic block model to this network, and each topic here is represented by a blue rectangle. If you look at the blue rectangle in the If we look at the blue rectangle in the center, we see that encapsulates, that's a topic that's very general and encapsulates all areas of research within the computer science area. As we move down each level of the hierarchy, the number of topics increases, however, they also become more specific. Below the bipartite network, we've shown word clouds that represent the third level of topics from the center. And here, word size corresponds to frequency. The significance of creating this new hierarchical structure of topics was that it gave us a more meaningful definition of what these topics really were, in that we were able to provide a measurable justification as to why a publication belonged to a specific topic. So now we apply this topic hierarchy to our data in order to better understand how topics evolved in terms of the institutions that were publishing them. We did this by plotting the topic distributions for each institution. Here are just a sample of the topic distributions that we plotted for 9 of the productive or highly publishing institutions. In these spider plots, each color refers to a different decade, and each axis in each spider plot refers to one of the 8 topics we previously saw in the word clouds. A point on an axis represents a proportion of the publications from that university that were published in that axis topic. And one thing that we can see here is that 2 different types of institutions start to emerge. There's institutions such as CMU that maintain a consistent structure over time, indicating that they remain equally consistently productive in the areas and the fields or areas that they're publishing over time. However, institutions such as the National University of Singapore and ETH Zurich have topic distributions that significantly change in shape over time, and this indicates that they're shifting their focus or the areas in which they are publishing a lot of papers in. While this is useful for analyzing the development of topics for different institutions, what we really want to understand is how movements within and between these institutions impact these changes or even the consistency of the distributions themselves. So we do this by studying the relationship of the authors that are arriving in an institution and how that relates to the variety of topics in which they are studying. or which they're publishing in. And we do this because we want to understand if academic affiliation exchanges promote academics to keep on publishing in increasingly niche areas of which they are already experts in, or rather if switching affiliations prompts them to start publishing in newly adjacent topics that the university is strong in. So what we show here is a CCDF of the number of different topics that an incoming author publishes in for each of the 9 universities that we showed before. One thing to point out is we enforced a baseline, only considering authors that published at least 10 publications in our data set, mostly because we wanted to focus on permanent members of academia. The second thing to note is that we moved from regarding the 3rd level of topics to the 4th level of topics, which included 55 instead of 8 topics. What we can see here is that with each passing decade, it becomes more likely for an academic to publish papers in more topics, which is consistent with studies that have shown, recent studies that have shown that collaboration in academia is becoming increasingly common and consequently leading to interdisciplinary studies. So in building our academic network, we could see a significant growth in publications that led to growth in network size. Additionally, we identified properties of our academic network that were consistent with small world network properties. And applying a hierarchical stochastic block model to our academic networks, we could detect communities and see how they evolved over time. We also analyze this with respect to country participation, noting that there's a high exchange of academics between US, Asian, and European countries. And finally, in studying the scientific growth of each, publications in the computer science research area, we assessed the development with respect to topic distributions for institutions. And then we also noted that incoming authors are more likely to publish in a greater variety of topics over time. We hope that our work in topic distribution inspires future work in defining institutions and characteristics that are ahead or behind the curve in terms of emerging hot topics in the computer science field or in any other field. Thank you for listening, and I can take any questions.
Thank you so much, Nandini. Very interesting work. I think you mentioned that the structures, the network of institutions based on affiliations maintain its structural properties over time. Isn't this stability related to the small rate of people being hired in the network? Did you do anything to kind of understand if the hiring position was too little compared to the overall network, that the structure would not change?
Right. So I think when we were talking about stability, we were referring more to the communities that were forming and the clustering that was forming through the networks rather than the actual, because the growth in scientific publications in itself is an indicator that the network size is not stable and is increasing as computer science became, like, publications increased as well. So I think it was the stability was more so referring to the clusters that were forming and like kind of the flow of academics, because the average flow of academics was around like 4. It flowed between 4 different institutions. So I think it was referring to those properties rather than the nodes and the hiring and how many like academics are being introduced into the network.
Okay, perfect. Thank you. So now I will ask Hugo to do his question, please.
Hi, Nandini. You showed a result about the change in the number of topics over the time as academics, they change institution. Did you also look at if, in addition to the number of topics, if the actual topics are changing? For example, if someone who moves from one institution to another, if they tended to shift the actual topics they are doing research in?
No, I think that would be like a good next step for our study, because this is just kind of like a preliminary look as to how these academic affiliation exchanges were impacting the topic distributions. So we did it solely based on like the magnitude of number of, like the topic variety, I guess, of what they were publishing in. But actually noting a distinct change, perhaps even going back to the third level, that kind of makes more specific boundaries between different topics so that we can see more significant changes. Because in the fourth level, because there are 55 topics, it might be a more subtle change if you go from publishing in one topic to two topics. It might be a very short jump, whereas if we were to consider third level topics instead, it might be easier to understand how a university's topics distribution prior to the incoming author arriving, how that impacts the actual, like if it significantly impacts the things that they're publishing in.
Okay, thank you, Nandini.
Thank you, Hugo. Thank you, Nandini. So now I will read a question from the chat. So would you consider relevant to overlap citation networks with your collaboration networks to understand if interconnectivity of topics institutions are related?
I think it would be interesting to consider in terms of maybe not necessarily defining a topic distribution solely based on the publications coming out, but also including the papers that are being cited by that institution. But I think I think that's one of the aspects in which citations could be included into the network. I'm not sure about, because you could primarily cite a publication that's from an academic that you don't have any sort of connection with. I might not directly integrate into the network, but I think it could definitely like be incorporated into understanding topic distributions.
Perfect, thank you. So now I will ask Diego to ask his question, please.
Hi, Nandini. So nice to see you again. I hope you're having a good time in your PhD at Exeter. So I really I'm fond of this work. I was just like thinking, if you had the chance and the opportunity to take this forward, to plan either a department, strategy, or a university strategy for, or even a country, as they plan for the next 10 years in terms of, what do they need in terms of these affiliations, right? And how to promote more organized, organized systems of education, right? If you had the chance to implement, this type of approach, have you ever thought about like implementation science of this? I think it can have a huge impact.
In terms of like the work itself, or in terms of like the standardizing affiliation names?
I would just spoke my mind here. Like if I were someone in charge of planning the 10 next years of an institution, right? I think I would be very interested in this type of work, because I would be able to understand how the world is doing, where this is leading the world in terms of this mixing of topics and so on and so forth, in terms of performance, in everything, diversity, inequality, anything. And I would be able to adjust, intervene to the plan for the next years, prioritizing specific areas, prioritizing specific hirings, I don't know, you name it, or fostering different mixing, using this as the guide for intervention in the university level, department level, country level, I don't know, you name it.
Yeah, so something that we did, but weren't able to kind of concretely get any sort of data or like concrete conclusions on, was we kind of compared university distributions to overall distributions of papers for each year. So we kind of found the similarity of these distribution shapes and distributions to like if we were considering a university in 2005, we compared it to all the overall distributions from like 2000 to 2010 in order to kind of see like where on the curve this institution lied. So I think in addressing like overall, we could, in finding patterns of how overall distributions of publications are changing, you can kind of see what's becoming more popular. Maybe in terms, if we were to like kind of going back to the other question, considering citations, we can kind of also see how like maybe not just in quantity, but also like in quality, right? Like we want to understand how topic distributions change in terms of like the quality of papers that are being cited as well. But yeah, that's one, like if we were doing this on an institution to institution level, that's one approach I'd definitely take, but it was hard to kind of get any generalizations out of it.
Thank you so much, Nandini. Thank you so much, Diego. Now we will move to the last presentation. So please, Nandini, can you stop sharing? Yes, the screen. And now Diego can start sharing his screen to start the presentation. Thank you so much, Diego. You can start your presentation. Sorry, Diego, we cannot hear you. Thank you.
First of all, thank you so much for the organization. I can only express my gratitude for moving us through these challenging times and allowing such a smooth presentation. It shows a lot of organization, really, and I would like to talk about this a bit today. CompleNet is one of the coolest conferences, and I hope I don't change that right now with these interesting topics. So the topic that I would like, so my name is Diego Pinheiro. My background is in computer science, and currently I'm a postdoc in the University of California, Davis, within the heart failure program, which is part of the Department of Internal Medicine. So just move. Okay, so promoting organized systems of care, because the title of the presentation is network-based delineation of health service areas. So I'd like to talk about promoting organized systems of care, right? And why this is important? Well, spending on health, right? When you think of spending on health relative to national GDPs of countries, the 10 highest income countries, you can think that it takes increasingly amount of the share, and it reaches 10%, some a little bit low, some a bit less, 11, 12, 9. But even in countries like the US, we are being an outlier, as 70% of the GDP is going to healthcare. And a major driver of this spending, and this is increasing over time usually, and not necessarily associated with increasing outcomes, clinical outcomes, but a major driver is chronic illness, right? It's a large proportion of the spending. And this is particularly important because we are now an aging population more and more, right? Survivals are increasing, and we live in a world of an aging population more and more. So among them, we are very interested in the heart failure, chronic related illnesses, and to think of how systems can tackle this problem, we can think of simple solutions, right? The one, Medicare, which is this large regulatory system in the US, creates ways of penalizing hospitals for overuse. A major problem when you don't have organized systems is that you just have people overusing the services, and then you just pay more for nothing. Right? And they just decide to penalize hospital if they have higher than expected hospital admission rates, right? And the thing is, they saved money over the years more and more, but they focus on this readmission, but then survival didn't necessarily got better, right? And then a lot of hospitals and communities in these specific conditions, here there are 6, from acute myocardial infarction to coronary artery bypass, pneumonia, and heart failure. And basically what they say is that, we're being penalized for issues beyond our control. And, you actually just, you maintain the current system, which somehow rewards reimbursement over quality of care, right? And you don't offer any pathways, right? You just penalize. And every year, the 3,000 hospitals in US, half of them pay penalties. They lose hundreds of millions of dollars. And they, at least once, all of them already paid that over this period that this was implemented. I'm just mentioning that because it's a simple solution. Just keep the system the way it is and try to penalize. It's a beginning, but there is some people, including John Wennerberg, he has been studying epidemiology of healthcare service delivery for decades, and he has this amazing book where he documented all his works, which in the beginning were not well received, but nowadays his idea spread and even create the major largest agency of funding the US for healthcare quality and research. Well, to make a long story short, right, he discussed all of these documenting this one unwarranted variation, these problems in the systems, blah, blah, blah. And at the end, he finishes his book talking about pathways to reform. And he acknowledged that we need to promote organized care. I mean, and of course, that will reduce overuse, but that requires new ways of thinking about how to organize and finance the system. And he himself, after documenting these 3 decades of his work, one of his earliest work dates back to 1973, when back then, you know, putting data together, integrating was not that convenient, but he did it anyway. And he integrated data of these multiple hospitals in Vermont and all its discharges. And he wanted to move from hospital specific way of thinking, right? Individual level or hospital level. And he was interested in thinking of regional level, but not, you know, not country, not state, and not county. He was interested in data-driven. He didn't use that word at that time, but it's a data-driven delineation of organization unit of healthcare patterns. And then he just used this data and then created these regions where hospitals are within, and then he could see variations in healthcare. Well, this leads to the largest atlas in healthcare in the US, and we also, I understand, we have the equivalent in the UK. But once we have these in place, they supposedly, these are more meaningful units for analysis of healthcare data. And then you can now try to create more homogeneous areas within each other, right? In which you can study variation, and some variation are expected, but some, you know, 19-fold variations, you know, if your kid lives in this county, he has 80% chance of having a procedure, but if he lives in another county, it just vanished. So some variation is expected, but some is higher than expected. This is kind of unwarranted variation. And this is a means to understand it. It's using health service areas. If we go those lines, we have basically this idea of promoting organized systems of care by creating these care coordination mechanisms. These are usually niche, this is specific, but they carry with themselves an idea of care coordination. These models, there is models in heart failure. You know, how can we make care more integrated, more connected, more accountable, more smooth, the transitions, you know, how can we integrate primary care and everything like that. And even the any nationwide attempt to provide an organized systems of care usually yields improvement in clinical outcomes. So this is gaining traction. And here in the title, I have this idea of network-based delineation, right? Because networks in healthcare, they have been used to understand interprofessional practice, how if you go to a hospital, how people, based on the notes, they interact with each other. And then you can create this network of practices interacting with each other. How a hospital inpatient services is provided, how you go from, you know, admission to the cardiology unit to the pediatric, and then you can kind of have a view of the hospital. How physicians interact with each other when they refer patients, and you can think of referral paths, and also how they share these patients, and how that leads to adoption of technology, of medical drugs, and so on and so forth. And even allocation networks of organ transplantation networks have been used to attempt to organize and understand care systems for a while. But recently, one of the first attempts to create a data-driven delineation of health service areas using networks was proposed by Hu et al. And basically, they just use this gold standard type of data for doing it, which is this hospital discharge data. And you basically have the zip codes from which patients come from and the zip codes of hospitals to which they go. And then you have a network of hospital patient discharge. And then if this is a network and if you apply a community detection algorithm, they apply the modularity optimization approach. The communities themselves are the health service areas. So, and then you delineated them, right? In their work, they show how this type of delineation can be superior to non-network based delineations, not only because now you have a network to understand and study and as a means to understand, but also in terms of the evaluation criteria, which they show some, and I would talk about on some of them as well. So, and then this gaining traction. A lot of discussion currently is on how this automated delineation of health service areas can become a new tool for healthcare planning, and this is somehow become more specific. So there are people only think about cancer, health service areas. There are people thinking of other types of networks, using networks, right? And in this work, at that time we were very curious on doing a comparative analysis of these different algorithms, right, and into this problem. So we basically use these hospital patient discharge networks in the work they did in Florida, but we had the opportunity in California because of the availability of data that I'm going to show just in a minute. And then we applied some algorithms, and then we have the areas, and then we could evaluate some metrics. So the data that we had was provided by the Office of Statewide Health Planning and Development, and they provide, is publicly available, they provide these different types of discharge. So for each of these discharge, you have discharge type, you have this number of data set here of discharges from these hundreds of hospitals and thousands of zip codes in California for these past years. And this is somehow how the data looks like. You have the hospital ID, the patient zip code, the year, the type of discharge, and the number, right? And we at the time, we are very interested in putting together the minimally sufficient diverse set of community detection algorithms, not only the Louvain, but also some algorithm that doesn't maximize modularity, but maximize this map equation of random walkers, the stochastic blot model because of the statistical nature, and even the label propagation. So we put these algorithms together, and among other metrics that we report in the paper, there are others, but one of them, it's interesting because it's a very simple way of thinking of what the area, internal validity of area is, which is the localization index, right? Which is basically the percentage of patients that live in this area and are treated in this area. That's basically what it is. So if it's 1, right, it's 100% of the population lives in that area and are treated in that area. And if it's 0, no one in that area is treated in that area. So usually we would like to find areas that have higher localization index. So basically we have these 4 discharge types, and for each of them we had 7 years. So we create these 28 hospital patient discharge networks. And then for each of them, we apply these 4 community detection algorithms, right? And these yield a total of 112 HSA delineations for California. In the paper, I mentioned more comprehensive about these results, but all the data, the code, and even the whole analysis is publicly available in the Open Science framework. We made sure to use some framework for modeling workflow. So all the data is there, all the data we actually acquired, we created, integrated, all the analysis, the networks built, all metrics calculated, plots, everything. You can either just pick it up, or you can just run again, since the data acquisition to the plots.
Sorry, Diego, you have 4 minutes. Sorry.
Okay.
Thank you.
So basically, I'm just gonna do some highlights in here. So we just put these algorithms together, and this is for the same year, for the same type of discharge. And what we see, we see a couple of things. We see the first feature is that some algorithms are better able, like the InfoMap and even the label propagation algorithm, they're better able to delineate contiguous areas. Past methods that are non-networks, they usually do so they usually define areas, and then they have an additional step just to ensure contiguity. But some algorithms in network-based algorithms, they kind of get in contiguity really, good naturally, right? Some better than others. So if you compare the Louvain with the informatic, you can see Louvain finds colors mixed, which means that they're putting areas mixed together. Also, some algorithms find more high scale, high granular, areas with high granularity, smaller areas. Others find larger, wide areas. So this is another feature. And if we compare the Louvain, like, of course, we would like to find the highest numbers of areas possible. So the Louvain find 20, and with a pretty high localization index. If it only found one, it would be 100%. So we would like to find more. On the other hand, the low-level propagation finds a lot of areas, but the internal validity of these areas go down a little bit, right? 7%. So basically, areas delineate from people that are not treated in these areas as often. But the InfoMap, for instance, can find almost 3 times more communities and kind of just lose a little bit of the localization index. So you have more means of meaningful units of analysis in terms of numbers, and they kind of preserve some internal validity. So this is some property. Another thing that we also observe is that the nature of the service provided, if you change from emergency department, which is more chaotic and planned, and inpatient service, which is more planned and less chaotic, the same algorithm, and this is consistent across algorithms as well, they kind of find wider areas because somehow this reflects the locality of the service. So this is some other features that kinds of come up on when you apply this. But basically, to sum up, health spending, chronic illness, and aging population, this has become more and more of a problem, and simple solutions will not solve it. We need to think of care coordination mechanisms to promote organized systems of care. And these community and network-based approaches, such as the ones to delineate these health service areas as the units of care coordination patterns, can help a lot that to happen, and become more meaningful units of analysis for healthcare data. And we saw just comment specific things on this trade-off between internal validity and the number of units that we find, and the existing heterogeneity among these model, right? We are just pushing forward these to study heart failure variation of practice and how these physicians are adhering to guideline-directed medical therapy within these areas and how this is related to outcomes. Just to mention, like, the people involved in this work, I'm really grateful for all of them, and that's it.
Thank you so much, Diego. I was wondering if instead of delineating the areas, wouldn't it be better to have, I don't know, fuzz classification of treatments? Like, instead of you have a fixed region where you would be treated, but depending on how many people you are treating in the area, you would be reallocated to some other areas. Like, you would have the borders being kind of present in more than one health service areas. I don't know, did you already think about it, this view, this perspective?
So I'm not sure if I understood correct, but it will be, instead of thinking of a fixed static definition of what the area is at a given time, it's thinking that doesn't exist actually, and then you can think of multiple ways, right? Is that what you're saying?
Yes.
I've never thought about that. Because first, like, we need to see where we are coming from, and we are coming from a disorganized system, like that is not even areas themselves. Mm-hmm. And then we are starting to thinking different than county, right? People, this is arbitrarily defined administrative units, and they not necessarily have to do with health as the way it is actually provided. And the thing here is what makes a more meaningful unit of analysis, and that's what it comes from. And when you think of implementing this, and you are a hospital, you need to know who what's the population you're serving, right? So you can be accountable. So we can think of ways we can make these, maybe that you're saying, happening, but we need to think of how can we also put accountability, like you know, you are hospital, you're not Sacramento, like the county where I live. Like Sacramento County, it's not an accountable area because the hospital in Sacramento, the hospitals in Sacramento, they treat people that is in other counties as well, right? It's kind of overlap, right? So in a way, this is somehow overlapping with the counties that we already kind of have. So when a hospital, for instance, study the needs assessment, right? They need to define a population. This population usually is used by the counties or something like more administrative or so. But we can think of now more accountable units of defining these areas. I'm not sure if I answered, but I hope I did.
Yes, thank you. So now I will ask Ronaldo to ask his question, please.
Hi, Diego. So thanks for the presentation. In fact, I'd like to just make a comment about the question that Mariana asked, right? So I think it's an interesting point in terms of if you have your area that you primarily served by and you remove that one, you could perhaps have a second layer, right? Where that you have the secondary area. So if that hospital, for some reason, I think doing dynamically may be quite hard, but you may say, if that hospital is overloaded for some reason, COVID, for instance, is there what is the second, in terms of preference, area that is responsible to serve me as a citizen, right? So, and perhaps you can do this by somewhat, when you define the regions, you say, okay, define another one that is not the one that was already defined, and what is the second best. But anyway, so but that's not my question. My question is this idea of areas is reminds me of the issue of gerrymandering. Are you familiar with gerrymandering? I suppose. Are you?
No, not that I am.
So in the US, I mean, you have to divide counties on where people vote, right? And gerrymandering is this artificial way that people, apparently, whatever party is in charge, they change the voting areas, and then you end up with this incredibly weird shape, right? And I think it's gerrymandering. So it basically means that you try to concentrate, let's say, all the Democrats or Republicans in one area by having a shape that is really, really weird, but it is contiguous, right? Because it has this. But if you actually Google later, you're going to see that you have this hourglass shape, right? That is, there's one road that links two areas. And the idea is that if you concentrate everybody that votes for a particular party in one area, they will win that one by 100%, right? So it's going to be 99-1. But then because it's a representation of areas, the other areas are all from the other party. So I wonder, first, could you end up with a situation like this when you actually start having define those areas that you have this very weird sort of shape? And second, could you use an approach, if you don't, could you use an approach to actually stop the idea of gerrymandering, or come up with an idea to divide where people should vote, or what is the contiguous area that makes that people will vote for using whatever you're doing? Does it make sense what I'm saying?
I think all makes sense. Thank you for introducing this concept. I wasn't aware about it. So first, I think we need to know what actually is, right? Like what is actually happening the most we can with the data we have, right? Not necessarily, because we need to remind ourselves where we are. We are in definitions that are very arbitrarily defined, they are not data-driven, even less network-based, if that's good, right? But we are coming from a view, you know, that we are in the arbitrarily defined, previously defined set of administrative areas usually. And then we need to see if actually that corresponds with what actually happened, right? And trying to answer the first question, I think, yes, we can come up with weird shapes. Not sure if that necessarily is bad or wrong in a sense, but, and from there, we can now think on how can we intervene to make the shapes we think are the desirable shapes, right? I mean, if those are not the ones that are appropriate, right? But I think the first step is shifting from, and even to push this idea forward with these agencies, right? We need to do this smoothly. First, shifting from the traditional way of doing it towards a data-driven network-based way. That's my opinion, right? And that's why we do these works, because we are trying to get and collect a lot of this preliminary data to put together a huge proposal, you know, to create this new atlas and to, anyway. And this is the first step. Now, what we have these weird shapes, we have these, inappropriate area, you know, where do we want to go? And then I think that's your point, and it's really, really interesting. If the areas we find doesn't have the properties, you know, that are desirable, we need to make them that way. And then comes control, comes intervention, right? And I think that's I think that's exactly what we want, right?
Thank you very much. Thank you.
Thank you very much, Diego. Thank you, all the speakers. Thank you for watching us. I think Ronaldo has something to say right now about the session tomorrow. So please, Ronaldo, you can speak now.
Thank you, Mariana. It's just a quick reminder that we will start again session 4 tomorrow at 10:50. So I appreciate everybody for joining. I know that it's hard to do those things online, particularly different time zones and so on. So I understand that some of you, I assume, like Nandini and Diego, is quite early for you, being in the West Coast of the United States. But unfortunately, there is no other way to do this. So I hope to see some of you tomorrow. We will do the same way. So we'll be here on Zoom, and we will also be broadcasting this live on YouTube. So thank you very much. Thank you for the chairs, Mariana, Anna, for running quite smoothly. And I hope to see you tomorrow. Thank you very much.
Thank you, everybody. Bye bye.
Thank you. Thank you, guys. Thank you.
Thank you. Thank you, CompleNet.